Welcome to Sweet Spot Maths, the gold standard for A-level maths teaching. I'm continuing in this video exam revision using Edexcel paper 1 from 2020, questions 10 to 13. I'm David Forster. The first question in this paper is a integration question using substitution. So we have quite a difficult substitution question. The question says use the substitution x equals u squared plus 1 to show that. It's a show that question. So we go through the various parts of the integral and we need to show how all of them change into the integral in terms of u. So the suggestion I will give is that we start with the hardest part of the integral, which to my mind is the bracket involving 3 plus 2 root x take 1. Replace x by u squared plus 1, we get 3 plus 2u, which is encouraging because the final integral has indeed a bracket with 3 plus 2u. Go for the next hardest part, x take 1, that will be u squared. We've got to convert the dx's into du's. A common mistake is just to write du instead of dx, which is not correct. So if we differentiate, we get dx du equals 2u, or dx equals 2u du. We must remember to change the limits too. Quite a common mistake is to forget to change the limits, or at least to show how they've changed. So x is 5 gives u squared plus 1 equals 5, u equals 2, and likewise x equals 10 gives u is 3. So going through the integral, we've changed the limits. On the top, dx has become 2u du. On the bottom, we have u squared times 3 plus 2u. One of the u's cancels, and we end up with the result that we've been asked to find. The second part of the question says, hence, using algebraic integration, show that. Hence means use the previous part. Algebraic integration means we're not looking for a calculator numerical answer, and show that means we're still looking for clear details. Now we're integrating a fraction. Unless it's a straightforward fraction like one of the results I've written at the bottom, where you can simply write down the answer, you're probably going to need partial fractions. And that's what I've done here. So I've split up the integrand into a over u plus b over 3 plus 2u. Clear away the denominators. I've decided to substitute in two values to find a and b, and this is the integral I need to do. It's now in a form where I can use the results from the bottom. So 2 over u integrates to 2 ln of mod u. Subtract. It'll be 4 times ln of 3 plus 2x, 2u modulus over 2. The 4 over 2 gives us a 2 here. It is a fairly common mistake to forget to divide by the a value. We now put the limits in, and we are asked to make it into the ln of a single number. So we use the laws of powers, taking the 2 inside as a square, and the laws of dividing, ln of a over b, to get the final answer, ln of 49 over 36. There will be some candidates who will not know how to take the lns and combine them. Make sure you know how to do that. Having a quick peek at the examiner's report, this question proved to be more discriminating than expected, with many failing to notice the partial fractions in part B. Remember, this paper was set in the aftermath of COVID, and it's possible that candidates weren't prepared as well as they might have been otherwise. But still, it's interesting how quite often the examiners are saying that the questions were found to be harder than expected. Part A was well answered by many candidates. Some students lost the final accuracy mark, and some did not finish their working with an expression showing the integral. A few made arithmetic slips in finding the limits, or did not attempt to change them at all. Of those who did use partial fractions, most found the values of a and b correctly. Unfortunately, many forgot to divide by the 2 when they integrated 1 over 3 plus 2u. A number failed to simplify the numerical logs to an expression of the required form. So that confirms the points we've just made. On to question 11. Now, question 11 has 2 circles, 2 overlapping circles, one of them with the equation x squared plus y squared equals 100, and the other with the equation x take 15 squared add y squared equals 40. And the question says, show that angle AOB equals 0.635 radians to 3SF. It's a show that question. Now, there are actually 2 sensible ways to deal with this. One is to find where the circles intercept, that is points A and B, and use that with some trigonometry. The other is to do what I've done here, which is to use the cosine rule. I know that the radius of C1 is 10, because 100 is 10 squared, so OA is 10. I know the radius of circle C2 is root 40, that is AC, and the distance from O to C is 15 because of the equation of circle C2. I want the angle I've marked as alpha, so cos of alpha will be 10 squared, add 15 squared, take root 40 squared over 2 times 10 times 5, which gives me 0.3176 radians, and angle AOB will be double that, which is 0.635 radians as required. The next part asks for the perimeter of the shaded region to 1 decimal place. So the shaded region is going round the larger circle from A to B, and then around the smaller circle from B to A. Perimeter using radians is r theta, so theta is going to be 2 pi, take away on the left hand side angle 2 alpha, and on the right hand side angle 2 beta. A common mistake in this question will be candidates assuming that alpha and beta are the same, which they aren't. So we need to find angle beta somehow. So what I've done is I've used the cosine rule again, as I did before, to get beta is 0.512. Therefore, the perimeter is, on the left-hand side, r theta, 10 times 2 pi take 0.635, and on the right-hand side, root 40 times 2 pi minus 2 beta. And that gives me a perimeter of 89.7. There are no units mentioned in this question, so it is just 89.7 units. A quick peek at the mark scheme. Well, there's the diagram that we had earlier. And comments here. This proved to be a challenging question, with few candidates achieving full marks. Part A, variety of approaches, including the 2 that I've mentioned. In part B, very common to see just the first mark scored due to many candidates wrongly assuming the given angle was the same size as the other angle that we wanted. Even the minority of candidates who found the angles correctly, getting the final answer proved a challenge, and only a very small minority managed this. Lots of opportunities here to make sure that we can do the things that other candidates can't. On to question 12. This is a trigonometry question, and the question says, show all stages of your working. Solutions retiring entirely on a calculator are not acceptable, so we have a show that identity. You can either start from the left-hand side and work to the right, or from the right and work to the left, and both of those seem to be perfectly reasonable approaches in this question. You must make sure that whichever side you start on, you have a full thread all the way through until you obtain the result on the other side. So I've started on the left-hand side. Cosec theta, usually speaking, if we get a cot, a sec, or a cosec in these questions, we replace them with 1 over the more standard function. So 1 over sine takes sine squared. Common denominator, 1 takes sine squared over sine, and we know 1 takes sine squared equals cos squared. Cos squared over sine squared is cos over sine times cos, which is cos theta times cot theta as required. Now, as I read through that, I sometimes said sine instead of sine theta. When you're writing this down in an exam, do not do that. Make sure you put the thetas in a show that question, just to make sure that you really are being accurate and showing all stages of your working. Part B, hence or otherwise. Hence means use the previous part. Otherwise means you don't have to. You could use a different method. The obvious one is to use the previous part. So we replace the left-hand side with cos x cot x. We've changed into x here instead of theta, equals cos x cot 3x take 50 degrees. We have cos of x on both sides. We want to cancel that, but we must think, could cos of x be 0? Yes, it could. And in this range, that would give us an answer of x equals 90 degrees. That is one of our solutions. Otherwise, cot of x equals cot of 3x take 50 degrees. We may fancy turning that upside down, reciprocating to get tan of x equals tan of 3x take 50 degrees. The first obvious answer is that x equals 3x take 50 degrees, but both cot and tan are periodic, with 180 degrees being their period. So in fact, we have the plus or minus 180 n degrees. Rearranging, we get 2x equals 50 plus or minus 180 n. So dividing by 2, x equals 25 degrees plus or minus 90 degrees n. A mistake sometimes run into is candidates working down to x equals 25 and then adding on the 180 degrees n. That's wrong. You add on the angle 180 degrees n or whatever at the point where you do inverse tan. So in the range we have 25 degrees or 115 degrees. And note at the bottom, cosec theta equals 1 over sine without theta is very much not okay. So a quick peek at the mark scheme, the examiner's reports. Part A generally answered well. Part B was often left completely blank. Many who attempted it failed to see the connection with Part A and got lost in complicated trig expressions which led nowhere. Don't overcomplicate. Of those who did use Part A, the most common solution was simply x equals 25, thus losing the solution given by cos of x equals 0. Only a small minority of the more able found all three solutions. Okay, question 13. This is on sequences. We are given a sequence of numbers defined by a recurrence relation or by iteration. A of n plus 1 equals k times an plus 2 over an, where k is a constant. Now, this is not an arithmetic or a geometric sequence, so we don't want to see use of those formulas in this question. We are given that the series is a periodic sequence of order 3, and the first term is 2. Periodic of order 3 means you've got A1, A2, A3, and then it repeats itself. Every 3 terms repeat. Not less than 3, every 3 terms. So the question says, show that this quadratic is true. We're going to use the periodicity for this. So A of 1 is 2. A of 2 will be 2k. A of 3 will be k plus 1. And A4 will be k times k plus 3 over k plus 1. Since A4 equals A1, we equate, we rearrange, and we get this quadratic. A quadratic which in fact has 2 solutions for k, being 1 or minus 2. Part B says explain why k is not 1. Well, if k was 1, A1 would be 2, A2 would be 2, A3 would be 2. It's just 2, 2, 2, 2, 2. That's not period 3. That's not order 3. And that's what you need for the answer. Hence, in this question, k equals -2. Part C says, find the value of the sum of the terms from the first to the 80th term. Now, we want to use periodicity here. We're not going to use any formulas for sums because it's not arithmetic or geometric, just common sense and arithmetic. So we have the first three terms, which are 2, -4, -1, which gives a -3. That is repeated 26 times up to A78. And then we have the last two terms, which will be A1 and A2 again. So we have 26 times -3, add 2 -4, which is -80. A quick peek at the examiner's report. This question proved very discriminating, with weaker candidates scoring only the first mark. But there were some excellent and well-written responses. In part A, applying the iterative formula to find A2 was achieved by most, etc. Fully correct proofs were rare. In part B, only a very small minority of candidates gave a correct and sufficient reason why k cannot equal 1. In other words, the period is not 3. When it says a question is very discriminating or was found to be hard, that might induce fear and alarm. But actually, with more able candidates, you can make these areas of difficulty, of weakness for under candidates, your areas of strength. And that is one of the principles of sweet spot maths. It is to do maths in the sweet spot, fine-tuned to achieve your A star without wasting time. And by looking at these hard exam questions and picking out the salient points, that's one way of doing that. Secondly, by shifting your perspective and thinking like a mathematician, learn from these questions. Every question you do, learn something for next time. And thirdly, you're learning those exam secrets, the gaps, mistakes, and omissions of most other candidates to get that examination edge. This is Sweet Spot Maths. I'm David Forster. If you would like more information about my Sweet Spot Maths courses, do email me on support@davidforster.org.uk and I'll be delighted to get some free information over to you. Thank you for taking part in this lesson.